And as we talked about last time, we are not really skipping 3, but a recorded lecture for chapter 3 has been posted. Make sure that you do watch it. You are responsible for obviously the information in there, and that will hopefully help keep us on pace here with the holiday coming up on Monday, by the way, in case you're not sure. We do have a holiday on Monday. So we are then going to go to chapter 4. Which should be, I believe, the last chapter for the first exam, right? So again, make sure you are working on the homework for these chapters as we go through them. Don't wait to the last minute. Otherwise, you might be disappointed and you're not going to finish. Yeah, so make sure you are working through that. All right, so last time we finally finished up chapter 2 talking about conversions density. So in this chapter, we're going to talk about really the atom. We're going to talk about, not in great detail, but we'll kind of touch upon some of the experiments that led to sort of our understanding of the atom and the different parts of the atom. We will then talk about some sort of properties of the atom, things like mass number, atomic numbers, protons, electrons, neutrons. I believe we will also hit in this chapter the periodic table, I think, Sunir. And we will finish up, I think, the chapter talking about mainly electrons and electron configuration. So there's a lot sort of in this chapter, and we should get started probably, I imagine. So let's talk a little bit about atoms and elements. And as we might have touched upon earlier on, atoms are really, as we'll see, sort of the basic representation of elements. And atoms, basically, as we will see, consist of protons, which are positively charged, electrons, which are negatively charged, and neutrons, which have no charge. Elements, as you can see from the periodic table behind me, you could think of it as really sort of the basic building blocks of kind of everything in chemistry. Different combinations of elements will give you different compounds. You can think of it kind of like the alphabet, right? I think there's still 26 letters, give or take. And obviously different combinations of those letters will give you different words that have different meanings. Same idea in chemistry, sort of different combinations of even the same elements will give you some different compounds, which will have different properties and give you some different sort of substances along the way. So when we talk about elements, a couple of reminders, there are also molecules. And again, a molecule is a basic sort of definition of pretty much all you need for that is 2 or more atoms together. So if you have a molecule, that's basically the definition. And what I mean by that is essentially it could be 2 or more atoms of the same element. It could be 2 or more atoms of different elements. But in order for something to be a molecule, that's pretty much all you need. It's just need 2 or more atoms of something that's basically united together. And that's oftentimes confused with another word, which is a compound. And a compound is also 2 or more atoms together, but it is actually 2 or more atoms of different elements. And that's a really important distinction, is the different element part. In order for something to be a compound, you do need 2 or more atoms of those different elements that come together. So what I mean by that, again, sort of tie it to elements. We could have elements like K, which is potassium, which is just by itself. There are certain elements, for example, like hydrogen, that how they naturally come by themselves when they are uncombined with anybody is they come as H2, which basically means there are 2 hydrogens together, is what the little 2 means there. So basically, hydrogen, when it is all by itself and not attached to any other anything else, it comes basically as a 2-pack, if you will. And because that basically is 2 atoms together, that is what is sometimes referred to as being a diatomic molecule. And again, di meaning 2, atomic meaning atoms. So it basically is 2 atoms that come together. So in the case, for example, of hydrogen, it is an element, and it also is a molecule because it meets the definition of a molecule. It has 2 or more atoms together. Now, when we think about hydrogen H2, it is not a compound, and it's not a compound because the only atoms that are in hydrogen is hydrogen atoms. It's the same element. So it is not a compound. What is a compound? Something that we all see today, H2O, a little bit of water, right? So water here is a compound because basically water is a combination of hydrogen atoms and oxygen atoms together. So it meets the definition of a compound because it is 2 or more elements that are together. We have hydrogen and oxygen. Water is also a molecule because it meets that general definition of there's 2 or more atoms that are together. So water is a molecule, water is a compound. Water is not an element because it is not just one element by itself, right? So there's hydrogen and oxygen there, so it's not an element. So something like water is a compound. It is a molecule, but it is not an element. So again, that is the general definition. Our definition is really of molecules versus compounds. I personally like to think of molecules as just really like a basic definition of all you have to do to meet that sort of qualification of a molecule is you need 2 or more atoms together. And again, it doesn't matter if it's the same element or different. But for a compound, you have that extra sort of additional requirement for it to be a compound. You need at least 2 or more different elements involved for it to be a compound. Any questions on that there? Yeah. It doesn't matter how they're bonded. We'll talk about when we get to bonding in our chapter or so, but you can have, for example, this is a compound here, and this type of bonding that we see in water is what's known as covalent bonding. They're actually sharing electrons in this particular case. There's also, for example, ionic bonding, which happens when metals and nonmetals together, something like sodium chloride. And sodium chloride is considered also a compound because there's sodium and a chlorine together as well. So they can, and depending on what comes together, and we'll hit that in, I think, in the next chapter, actually. Yeah. Other questions? All right. So when we talk about elements, we do want to use the correct symbols. And typically, as you can see on the periodic table behind me, or have you seen probably on the periodic table, basically the symbols are really one of 2 sort of formats in terms of how they are written. If it is a 1-letter symbol, that 1 letter is always capitalized. So if you had, like I wrote earlier, potassium, which is K, you always capitalize the single letter by itself. Now, if you have a 2-letter symbol, which is really the other sort of symbol combination that you could get, we always capitalize the first letter, but not the second. So like we have here with aluminum, we would have a capital A and a lowercase l. So when you do write the symbols, it's really important to follow those rules. Now, if you're somebody that likes to capitalize everything that you write and only use capital letters, that's really problematic if you're writing formulas. So for example, if I write capital C and capital O versus capital C and lowercase o, the one on the left there, which is capital C, capital O, that is carbon monoxide, which is very different than the one on the right, which is the element cobalt. Yes. So you want to make sure that you do not write capital letters for all symbols. Even if you write everything capitalized, don't do it here because you'll probably get an X just like that there. You don't want that. So you might be actually writing something you're not meaning to do so by just capitalizing. So it's really important to make sure, again, if it is a 2-letter symbol, only capitalize the first one and lowercase on the second letter. And if it's a 1-letter symbol, you then would just make sure you capitalize that. Question on that there. Now, elements, as I mentioned, are pure substances. They are pretty much as far back as you could go. So, for example, we talked a little bit there about a compound. You could take a compound and you could do a chemical reaction with it, and you could break it back into its elements. So we had our water there. So you have your water. You could run an electrical current over the water there and do a little electrolysis, break it apart into hydrogen gas and oxygen gas. It's like a chemistry class. I'll do a little balancing there. But you basically can take something like a compound and through some type of chemical means, like a chemical reaction, you could break it back into its elements. We also see here as well, in addition to hydrogen, oxygen also comes in its natural state as a diatomic molecule. There's actually 7 elements that come naturally as 2s. Those are hydrogen, oxygen, nitrogen, fluorine, bromine, and iodide. So those 7, again, the way that they come, when they are uncombined with anybody else, they come as 2s. So, and they also come as 2s, not that it's necessarily that important in terms of their formula, but they come as 2s bondedly different. So like hydrogen comes as, for example, a single bond. Oxygen actually ends up as a double bond, and nitrogen ends up as a triple bond. And when we talk about bonding, we'll talk about why that all ends up that way. But they actually come differently bonded as well. But the main thing is they always come as 2s. So if you ever see anything in sort of words and you need to eventually turn it into like a formula or something like that, and they say hydrogen gas, that's H2. They say molecular hydrogen, molecular oxygen, that is H2O2. Again, that's how they naturally come. That's pretty much here on the periodic table. We got our hydrogen, our nitrogen, oxygen, and this down this group basically there. So kind of from here over and down the group on the periodic table, that's where you find all your 2s. By the way, pretty much everybody else on the periodic table comes as 1s, pretty much. So they all come as 1s, which are known as being monoatomic. They come as 1 atom basically together. While we're speaking of that, and we'll talk about it in a second as well, I'm sure, but a little reminder, just in case you don't know, we'll eventually start talking about things that have charges. But if you have any element off the periodic table by itself, once again, uncombined, not attached to anybody else, they don't have charges. So they're all neutral. Things, as we'll talk about again in the next chapter, only really gain charges when they start hooking up, mainly metals and nonmetals when they come together. That's when they really start to form charges. But if you had, for example, a piece of copper metal, it doesn't have a charge. It's neutral, basically. So anything that basically you pull from the periodic table is essentially neutral, unless obviously it reacts with something else that could give it a charge. Any questions on that there? Now, as I mentioned, you could break compounds into elements, but that again is as far as you could go. So you can't break it apart any further than elements. And again, that's kind of your basic units there. So here are some of the symbols for some elements. And again, you can see the combination there of either a 1-letter symbol, which is capitalized, or a 2-letter symbol where the first one's capitalized letter and the second one is not. Really, the names and things for these elements come from a wide variety of sources, kind of planets, as you can see. They also come from scientists' names. They come from places where they came about, philosophers, all these type of things, right? It's how we get, elements like Californium. I'm assuming it comes from California, right? Berkeleum, maybe up at Berkeley, you know. We have nobelium, einsteinium for some, scientists and stuff like that. So they do come from a wide variety of sources, and that's maybe why sometimes some symbols that you see, you maybe are wondering, like, where's that come from? Like, for example, lead. Lead is Pb, nothing with an L, lead, right? So lead is actually Pb. For example, iron as well. Iron is Fe, right? And obviously that doesn't perhaps make sense, but it is from the root of sort of where they come from. What should you know in terms of symbols? Well, you should know, I was going to say all of them, but eventually maybe not. I'll be honest with you, when you look at the periodic table, we deal a lot with kind of to the left. We do deal with to the right. And I would say kind of up here and over and down. We don't do too much with the bottoms here, and not too much in like this area here, but definitely left, right, kind of top, and then as you go to the right, kind of angling down, we kind of hit the. I would, if you haven't done so already, I would start really taking a look at the names that go with the symbols. Not necessarily that you need it extremely a lot in this particular chapter per se, but the next one we're going to get into will involve talking about naming things. So there's obviously rules to how you name everything. And if you're still trying to figure out what symbol is what, it's just going to make it a lot harder. So I would, from now, until we kind of get into that next chapter, I definitely would try to get some handle on, some of the symbols and their names that go with it. It's just going to make kind of when we get to the naming part, hopefully a little bit easier. You will obviously be given a periodic table that does not have the names. Yeah, so we'll have the symbols. So again, you need to kind of know, what the symbol and the name kind of goes with. So again, carbon, which I did good. I usually say copper and copper, carbon. So carbon C there, sulfur S, nitrogen N, hydrogen is obviously H. We do a lot here over here with our fluorine, F, chlorine, bromine, iodine, sulfur, phosphorus, aluminum, silicone. So again, like I said, a lot of these over here, we do touch upon. And in this area as well, there's our lead, which is Pb. Sn is tin. Sb is antimony. Bi is bismuth. So those we pop up. And then over here as well, gold, Au, right? Silver, Ag. Mercury also, Hg, pops up a lot. And like I said, zinc, Zn, copper, Cu, cobalt, as we talked about. So again, getting some familiarity with those. My favorite element, number 34, selenium, right? Never know where that one pops up. So make sure, you start getting that sort of understanding. So again, here are some of the symbols, and it will definitely make the kind of naming part that we get into a lot easier if you have some recognition of it. And again, as we were talking about iron and lead, those are again really where those symbols come from, those sort of common names, Latin names that are used sometimes to for the symbol, also for copper as well. That is again sort of where it comes from. All right, so here's a few other ones there. All right, so let's take a look at some of these, just may help. So we want the symbol for each of these. So iodine is I, yeah. Iron is Fe, magnesium, Mg, zinc, Zn, lithium, Li, yeah. So again, one letter capitalized, two letters, first one capitalized, second one not. There we go. All right, so try some of these names. So P is phosphorus, yeah, so that's phosphorus. Ar is argon, that's a noble gas right over there. Mn is manganese, not to be confused with magnesium, right, which is Mg. So Mn is manganese, right about there, number 25. Be is beryllium, and K is potassium. So again, like I said, you definitely probably sooner rather than later want to, again, get some familiarity with the symbols and the names that go with them. Again, it's just going to make kind of everything a little bit easier as we get into sort of, I won't say real naming, but real naming. Yeah, when we get into how you name everything else, basically. Any questions on there? Okay. So let's talk a little bit about the atom here and the structured atom. We're going to kind of touch upon some ideas and concepts that really helped us understand, what the atom sort of looks like. As I mentioned previously, the atom basically is made up of 3 subatomic particles, which are protons, electrons, and neutrons. And really, and neutrons have no charge. So really, a lot of the discovery of the atom came about after a few theories about, what atoms were and sort of what they were made out of. And the idea of the atom, as we talked about, is again really your basic representation of any element that you have. So any element that you may have, basically the representation of that element is basically an atom. And a long time ago, a guy by the name of Dalton, John Dalton, he came up with a theory on sort of what atoms were. And these are some of the parts of his atomic theory. And in the case of a theory, as we talked about, I think there in chapter 1, a reminder that a theory is something that maybe is not 100% correct in all aspects of it. It may be thought to be correct, and then maybe further experimentation down the road might disprove some of it, may prove some of it correct and some of it incorrect. And that happened actually with Dalton's atomic theory. So he basically said that all matter is made up of these tiny particles, which are called atoms. And one of the ideas from Dalton, and even really before Dalton, was sort of this idea that atoms are sort of indestructible. And you can't really do too much to them. And the idea of that is one of the ideas that are sort of not necessarily correct. And with the sort of idea of nuclear reactions, you can sort of change one element into something else by changing what's in the nucleus and stuff like that. So that part of it is not so correct. It is correct, the idea that they're made up of these tiny atoms. That's correct, part of it. He said that all atoms of a given element are identical to one another, and they are different than atoms of different elements. So also part of that is correct, and part of it is not so correct. So the part that's not so correct is all atoms of a given element are identical to each other. The existence of what are known as isotopes basically disproves that idea. And the idea of what isotopes are, they are different. I'm sorry, I say it right. They are the same element, but they have different masses. So even though they're the same element, they actually have different masses, which means they clearly cannot be identical to each other because they have different masses. So that part of Dalton's atomic theory is also sort of incorrect. The idea that every atom of the same element are identical to each other. Now, the second part of that is okay, the part where it says that an atom of one element is different than an atom of another. So if you had a copper atom versus an iron atom, there are differences in those two. They are not identical to each other. So that part's all good. He also said that atoms of 2 or more different elements combine to form compounds. And that is correct. A particular compound is always made up of the same kind of atoms and the same number of each of those atoms. So an example of that is water, right? No matter where you get your water, It ultimately is two hydrogens together along with an oxygen, pretty much, right? May cost you more depending on how it's bottled, but it's pretty much H2O, right? The core of it, what it is. And no matter where you go, if you have water, because hydrogen is essentially 2 grams or 1 gram, and there's 2 of them, so 2 grams of hydrogen for every 16 grams of oxygen. No matter where you find your water, you will always have a ratio of, for every 1 gram of hydrogen, you'll have 8 grams of oxygen present because of the mass ratio. The other important sort of idea of Dalton was the idea that a chemical reaction only involves the really recombination of elements. So in a chemical reaction, we do not lose any elements. We do not make new elements. Whatever we start with and whatever we finish with are the same elements. They're just combined differently. So what that means, for example, is if we have an arrow, and this is our reactants, which is our starting materials, say in a chemical reaction. And let's just say we had 6 carbons we started with in a variety of things. So there's a total of 6 carbons on the left-hand side of the arrow. When we're done and we make our products, which is what is made as a result of a chemical reaction, you will still have those same 6 carbons on the left-hand side of the arrow and the right-hand side of the arrow. They will be in different compounds probably, or different substances, but you will still have basically the same amount of carbons on the left-hand side of the arrow and the right-hand side of my example. That is what is sometimes referred to as the law of conservation of mass. We don't create nor destroy anything along the way. That's also who you could thank for when you have a chemical equation, why you have to balance it. So you have the same number of elements on each side of the arrow. So in a normal chemical reaction, as we'll talk about, pretty much it only deals with bonds making and breaking, and that is actually only electrons are involved in that. So only electrons are involved in that process. And that is different, though, than nuclear reactions. In a nuclear reaction, all you do is play with what's in the nucleus, and you change things all day with doing that. And that's why in nuclear reactions, you don't have that conservation of elements. What you start with and what you end with are very different things, very different elements, because you're actually changing what's happening in the nucleus. But what we deal with in here, since we don't do the nuclear chemistry chapter anymore, we won't deal with it at all. But we only deal with chemical reactions here. So we have that conservation of elements in a chemical reaction. However many, one element you start with on the left-hand side of the arrow, you should end with the exact same amount on the other side. And the idea of the conservation of mass is a simple one as well. Since carbon is 12 grams and you have 6 of them, you should also have at the other side of the arrow 6 times 12 grams conservation of mass of your elements from your reactant side to your product side. You'll have the exact same mass of each of those guys present. Now, as I mentioned before, atoms were believed to be very small, and they are. But even though they are really small things, they are made up of even smaller particles, and those are our subatomic particles, and that's our protons, electrons, and neutrons. So we have atoms, which are the basic representation of elements, really small things, and they're made up of even smaller particles, those 3 types of particles which have those types of charges. So along came this idea of trying to explore the atom and understanding where these sort of particles maybe are. And one of the really important sort of concepts in chemistry, and was also really important in sort of looking at the atom and exploring the atom, is the idea of opposites attract. And opposites attract, as was sometimes referred to as electrostatic attraction. Basically, opposites attract, right? Much like in life, right? If you have 2 positive people, that's a lot of positivity to be around, right? And if you have 2 negative people, that's a lot of negativity to be around. They say you want to try to find something that balances you out. So slightly positive, slightly negative, nice mix right about there. So same thing happens in chemistry. If you have something that has a positive charge and a negative charge, they will be attracted to one another. So positive things and negative things are attracted to one another. That is what is referred to as electrostatic attraction. If you have negative and negative things near each other, they definitely do not want to be near each other. They will repel each other, like we see here. They will try to get away as far as possible. Same thing with positive and positive. You have two positive things near each other. They also are going to try to get away as far as possible. But you throw a positive and negative thing together, we're going to kind of stick together. It's going to stick, and they will be attracted to each other. That is probably in chemistry one of the strongest attractive forces you could have, like an electrostatic attraction, positive and negative coming together. Sodium chloride, which is NaCl, is held together by that type of attraction. You ever heat up salt, you could heat it all day. It will never come apart and make gas. They will stay together. It will just start melting before it tries to go into the gas phase. So it's an extremely, extremely strong attractive force, that sort of opposite attraction that occurs. So how is that helpful when they were sort of looking at the atom and trying to sort of explore the atom? Well, what a lot of experiments used when they were doing that was radioactive particles, and three types of radioactive particles that were used in a number of experiments. One is an alpha particle, that's the symbol. An alpha particle is a positively charged radioactive particle. It is essentially, that guy right there is essentially helium, is basically what it is. They also use beta particles with that symbol there. Beta particles are negatively charged radioactive particles. And they also use gamma rays. And gamma rays have actually no charge. And they are really pure energy. They are extremely strong in energy, as we might see a little later on in this chapter. It is a very strong energy that comes off. If you ever work with anything that is a gamma emitter, you need a lot of protection to protect yourself, and you shouldn't be around it all that long. So a lot of experiments really took advantage of these charges, and why having things that have charges is really important is you could also use something like an electrical field. If you had an electrical field, there's a positive and negative sort of side to that field. And if you were to, for example, shoot a particle through an electrical field and you saw the particle kind of bend towards the positive side of the electrical field, that would probably tell you the particle has what type of charge? Negative, right? Opposites attract. If you shot a particle through an electrical field and it kind of bent towards the negative side, then you know probably that guy is positive. And if you shot it and it just kind of sailed straight through, ignore my non-straight line there, but it went straight through without moving one way or the other, I probably had no charge as it was unaffected by an electrical field. A magnetic field works the same way. There's a North Pole, South Pole, does kind of the same deal, kind of bend one way or the other, depending on the charge. So a lot of experiments when they were sort of exploring the atom used sort of this idea and this sort of discoveries to their advantage. And probably the earliest sort of exploration of the atom was one done by J.J. Thomson. He used what is referred to as a CRT, which is known as a cathode ray tube. And a cathode ray tube you may be familiar with. Used to be like old TVs, yes. Maybe some family members or you have some. They used to be on the floor. You used to call the TV repairman. They opened up the back of the TV and actually repaired like the picture tube. None of the TVs we have these days. Nothing. None of these guys, no. But those all had picture tubes. They were CRT tubes in there. Even computer monitors used to be CRT monitors. Those are the ones that have like the big back in them. Maybe you've seen them in the picture or something like that. Again, not this. That is not. That's why years ago, parents used to say, don't sit in front of the TV. You're getting shot by all those rays. Because it had an actual picture tube in there that was doing those things. So the CRT tube is basically this idea. It is a tube And it actually has charged plates on one side versus the other. So it has a positive side and a negative side. And it actually was a stream of negatively charged particles, like an electron, which would actually start moving this way, away from the negative side towards the positive side. And on this side, they would coat it in the screen, and you could actually see where it's actually hitting and stuff like that. So Thomson did a lot of experiments with the CRT. A guy that followed them up was a guy named Milligan. Milligan did what is known as the oil drop experiment. And basically, that experiment also takes advantage of sort of an electrical field and charges. He had a chamber where there was an electrical field. And what he did, much like the title implies, he shot oil into it and basically heated it up, atomized it. And what he would have was like a little opening where a drop of oil would go through. And as that oil was dropping, it would gain a charge through friction. And what he was able to actually do was like dial in the electrical field where essentially he was able to suspend the oil droplet. Basically, kind of dial it in. It wouldn't fall, it wouldn't go up, it wouldn't go down. And those two experiments were really important in terms of understanding the electron. And what we were able to understand in terms of the electron was Thomson figured out the charge to mass of an electron. And Milligan actually figured out what the charge was on an electron. And the importance of really those two experiments was if one figured out the charge to mass and one figured out the charge, we could do a little dimensional analysis there. We got the charge divided by the charge to mass of an electron. Charges cancel, leaves us the mass of an electron. And so from those experiments, they were able to figure out the mass of an electron. And it roughly is 9.09 times 10 to the minus 28 grams. Some books now like to round up to 9.11, but we'll go with 9.09. Is that a large number or small number? It's a really small number, right? It's like 28 places to the left and add a bunch of zeros, right? So it's a really, really small sort of number. So a really good understanding of the atom was really started, especially electrons, through these two really important experiments. And they were able to figure out really the mass of an electron. And what happened was after these sort of experiments, the idea was this. They knew obviously that the atom contained electrons, which are negatively charged, but they also knew that the atom was neutral. So they knew at this point that the atom had electrons, but it was neutral, which means in order for it to be neutral and it has negatively charged electrons, there has to be some type of positive component to the atom to balance out the negatively charged electrons. So what this led to was really a early model of the atom, which was done by Thomson, and it is what is referred to as the plum pudding model of the atom. Plum pudding is like a kind of rice dessert there with raisins and pudding, and the raisins are kind of in the pudding. And the idea of what they said was, all right, we know it's neutral. It's got to have some positive charge somewhere. So as the picture you see down there shows, it basically what they thought was all the positive charge was pretty much just diffused over the entire sphere. So you have the sphere, a positive charge spread out all over it. And embedded inside this sphere, like the raisins in the pudding, are the electrons. So you got all these electrons that are embedded inside. And they also felt at this point that most of the mass of the atom was the electrons. So this was sort of an accepted theory of the atom at this point based off of these experiments and what has happened before, that we have this positive charge that's spread out all over the place. And we have these electrons embedded in the pudding there of positive charge, and most of the mass of the atom is made up of these electrons. And as we talked about in terms of models or theories, they're only as good until they get disproven, right? And that is actually the case here. Along came really the next big experiment that really helped us understand truly what the atom looked like, or is basically made out of. And this was done by a guy named Rutherford, and Rutherford did the gold foil experiment. And basically, what it sounds like is he took alpha particles. So remember, these alpha particles are those positively charged radioactive particles. And he basically shot them at pieces of gold foil and other atoms. Now, the idea of what they thought was going to happen based on the plum pudding model to what they actually saw happen was very, very different. So, if we think about sort of the model of the atom that they were thinking about, which was we have all this positive charge spread out, we have these electrons that are embedded inside, and we're going to basically shoot these alpha particles, which are positively charged particles, at a big pudding of positive charge, right? So, what they thought would happen would be kind of this. We're obviously shooting something positive at something that's ultimately positive, which means they should repel each other, except that the positive charge is spread out all over, right? So it's not really thick, if you will, right? It's kind of a thin positive layer, if you want to think about it. So kind of like my paper here, if this was the atom, nice thin positive charge all spread out. If I were to hold this paper on one side and really held it tight on the other side, and I shot like a pin or something at it, it's moving really fast, right? It's heavy, and I shot at it. It's probably going to be able to pop through the paper, right? But as it does, it's probably going to deflect a little, right? As it's able to go through there. And that's what they really thought was going to happen here because these alpha particles are heavy, they're moving really fast. They felt that when they shot these things, it should kind of go through, but there would be some deflection as it went through it because again, you got positive and positive, but again, it's moving really fast. So kind of just a little bit of resistance as it kind of pops through the spread out positive charge. And they were very, very surprised when they actually did the experiment. When they did the experiment, this is pretty much what they saw. Most of the particles just sailed right through, no problem. But what they also saw was every so often, they would see an alpha particle bounce off at really large angles and even like head back to where they came from. I imagine if you were standing there, not so great, but bouncing off these really, really large angles. So that told them a couple of things that was really important about the atom. The first thing that it told them was perhaps this plum pudding model not so good, right? Because we clearly didn't see what we expected, right? If we had this nice diffuse positive charge, we should see those guys pop through no problem. Nobody should be bouncing off at these really large angles. They should pop through with a little bit of deflection as they go through it. They shouldn't be coming back to us. They shouldn't be bouncing off at super large angles. And that's what you see here. Again, most of them went straight through, but every so often they would see these guys kind of bounce off at really sort of large angles. So they wanted to think about sort of what they just witnessed when they did this experiment. So let's think about it. If I were to throw my pen that way with nothing in front of me, my pen is just going to go straight, basically, right? And that's what they figured out. They figured it out that pretty much all those alpha particles that just went straight through, no problem, pretty much hit nothing. Nothing got in its way, right? So had no problem going straight through empty space. But now, what would make an alpha particle jump out at a super large angle? It had to hit something that was very, what type of charge? Positive charge, right? Alpha particles are positive, has to hit something that's really, really positive. Not just positive, but super densely positive to make that really fast moving alpha particle bounce off at that super large angle, right? That thing is heavy and it's moving fast. So it had to hit something just as densely positive to make it ricochet basically off at that big angle. So they said, well, we have to really throw out the plum pudding model and go, clearly the atom is mostly empty space, which accounts for why all those things went through no problem. And maybe our positive charge is not spread out all over the place, but maybe if I took my paper, my example, and I folded it right, all my positive charge down, which theory, you just fold your positive charge if you need, right? You keep folding, where they say 7 times you can't fold anymore or something like that, right? 7 folds and you can't do anymore. Now, if all my positive charge was all concentrated in this area, right, and I take my pin and I throw it, it most likely is going to bounce back at me, right? Because it's not going to be able to pop through. It's just too much positive charge in there. And that's basically what they discovered from their experiment. They decided that the plum pudding model was really not correct. So they had to come up with this sort of new model of the atom. And basically what they said was the atom is mostly empty space. So Rutherford basically said mostly empty space. It also must contain a pretty dense positive core that they called a nucleus. So it has a dense positive core known as a nucleus. And in that nucleus, it was later found to contain protons, which are positively charged. And later on, like in 1930s, 1932, for example, it was found to also contain neutrons, which have no charge. And the other difference between sort of the plum pudding model and really this model of the atom was instead of the electrons being most of the mass of the atom, most of the mass of the atom was the nucleus. So most of the mass of the atom is the nucleus, and we'll talk about in a second why that is as well. So really their model of the atom is we have kind of this nucleus, which is really positively charged, again, contains protons, later, not at this time, contains neutrons. We have our nucleus. And traveling in that empty space is where we find our electrons. So that empty space is sometimes referred to, sometimes as the electron cloud. And we have electrons traveling out from the nucleus at some point. By the way, as we'll talk about, electrons do not travel in pretty circles. They travel randomly about the nucleus. They don't travel in pretty little circles and orbits and stuff like that. They travel really randomly about the nucleus. By the way, should there be any attraction between the electron, which is negatively charged, and the nucleus, which is ultimately positively charged? Is there attraction there? There absolutely is. It's why your electrons just don't leave, right? They're kind of stuck to it like a rope, basically, right? Some electrons are strongly attracted to it. Some are still attracted to it, but not as strongly. And the distance at which these electrons are traveling from the nucleus accounts for whether or not, for example, they're involved in bonding or not involved in bonding. There are certain electrons that are involved in bonding, which are the ones that are furthest away from the nucleus. Because they're further away from the nucleus, they're still held, but they're not held as tightly as those electrons that are much closer to the nucleus. They're like feeling the full brunt of that positive charge, and they're held a lot tighter. So that's what accounts for, as we'll talk about, why only certain types of electrons, for example, are involved in bonding and others are not. Any questions on that there? All right. So there we go. We got our nucleus, protons, electrons on the outside, neutrons in the middle, and protons in the nucleus. In terms of mass, we talked about the electron. And again, it was like 9.09 times 10 to the minus 28 grams. Just to kind of give you a reference, our protons were found to be in the ballpark of 1.673 times 10 to the minus 24 grams. And our neutrons were found to be 1.675 times 10 to the minus 24 grams. Actually, it is the neutron out of all three of those subatomic particles, which is actually the heaviest, just slightly beating out the proton. Proton and neutron very close to each other, but the neutron is actually the heaviest, followed by the proton in terms of mass. The electron is about 1,800 times lighter than any proton or neutron there is. So the electron is much, much lighter than those other two particles. That also reinforces the idea of Rutherford, which is most of the mass of the atom is made up of the nucleus. And that is because in the nucleus, you have both of these guys there. And each one individually is about 1,800 or so times heavier than any little electron that's flying around. So that's what makes sense that most of the mass of the atom is actually made up of the nucleus. Any questions on that there? You could think of the atom as, since we just saw the Super Bowl, the Superdome. Yeah, like the Superdome there. And the nucleus is like a marble on the 50-yard line. Yeah. So super small volume, the nucleus. Super large mass, though. Yeah. It's the most of the mass of the atom containing a very small volume of the atom. Most of it is empty space as things are flying around. Any questions on that there? Okay. All right. So which of the following is found in these descriptions? The one we find outside the nucleus is? It is the electron, right? The one that has a positive charge is proton, and the one that no charge is, right. And again, neutrons, like I said, actually were only discovered in 1932, really, basically. A guy by the name of Chadwick discovered them. He did a lot of work, and what he saw actually happen was a lot of radioactivity coming off, very similar to gamma rays that have no charge. And again, that's, if you think about that alpha particle, kind of similar to a proton in terms of charge, beta kind of like an electron, which is essentially what a beta particle is, and then a gamma ray is very similar to a neutron, no charge. So again, that's why those sort of radioactive particles were really important in discovery of the atom. In each of the following, true or false, the mass of an electron is greater than the proton. It is false. Again, it's about 1,800 times less massive. Protons have positive charge, electrons have negative charge. That is true. The nucleus of the atom contains only protons and neutrons. That is true in that case, right? Again, electrons are not in the nucleus. They are outside of it flying around. Any questions on that there? All right. So there again is the picture, like I said before. I guess it kind of shows up there. This kind of bluish area here, there's kind of like a darker area here, and then it kind of gets lighter as you get away from the nucleus. That again is what is sometimes referred to as electron cloud. And as I mentioned, because electrons really don't travel in these fixed orbits or anything like that, they travel in what are known as orbitals, and they are basically probability maps. And that's what this sort of picture is. Sometimes you'll see it as like a reddish type of color. And basically, when you look at it, the darker areas are a higher probability of finding an electron. Kind of the lighter areas of the color is a less of a probability of finding an electron. So you can see, if you kind of see it up there, but the darkest kind of blue is right around the nucleus, which makes sense. Again, the nucleus being positively charged. So there is a pretty good probability that you should be able to find an electron near it, since it is negatively charged. As you again fan out away from the nucleus at some distance, gets a lot lighter blue in that area. It means that there's still a possibility of finding an electron out there, but obviously less of a probability than if you're really next to the nucleus. For sure, you're going to probably come across one. That still means I don't know how the electron got there. I don't know where it's at actually, or how it's moving. That is what is known as the Heisenberg uncertainty principle. A particle like an electron, the more you know how it's moving, the less you know about its position, and vice versa. The more you know about its position, the less you know how it's moving. So when we talk about electrons moving around, that's why we don't kind of follow the Bohr model of the atom, which is that orbital model where everything goes around in a pretty little circle and stuff like that. It doesn't actually travel that way. But the best we could say is, I think in this area, there's a good chance of finding an electron, but I'm not really sure where it is or how it got here, if it does get here. But there's a good chance at some point you might run across an electron, rather than like the sort of Bohr model, which is that orbital model where it's in this orbit, it's going around in circles. You kind of put your finger there, eventually it'll come back around, right, and hit it. And again, they really don't travel in that sort of fashion. All right, any questions about the atom and how we got to it? So you should know a little bit about, again, those kind of experiments to the level which we talked about it. You should probably know the early model of the atom, which is the Plum Pudding model, and Rutherford's experiment and what came out of it, which is really sort of the modern version of the atom. Protons, electrons, neutrons are, and what sort of came out of it. Any Okay, we're going to continue on here. Now that we've talked about how the atom sort of came about, if you will, I guess, or really the discovery of sort of what the atom looks like, we're going to talk about some properties of the atom, including atomic number, mass number, and isotopes. And when we talk about atoms, now that we sort of understand what they sort of look like, a lot of the atoms, sort of chemistry does come from electrons. They're really involved in chemical reactions, making and breaking bonds. If you just think about sort of the atom, we have our nucleus, which is positively charged. We have our electrons on the outside. So if you had two atoms, really, if they were to come together, really the electrons are going to be kind of the first ones they're going to say hello to each other as they're on the outside, and they're going to interact with one another. In any chemical reaction like we talked about in this class, as I mentioned, it only involves electrons and bonds, and it has nothing to do with the nucleus. And that's again why I was mentioning earlier, there's a conservation of elements, because we don't do anything to the nucleus, just those electrons. So one important sort of definition is the atomic number. And the atomic number is sometimes abbreviated with a Z. And the definition of the atomic number is it is the number of protons there are in an atom. So basically, this number of protons there are in the nucleus of an atom is the definition of the atomic number. Now, since we just talked about the atom, and we know that really every atom pretty much is made up of protons, which are positive, electrons, which are negative, and neutrons, which have no charge. If we know the number of protons, which is the atomic number, and the atom is neutral, which means overall it has no charge, it will also tell us the number of electrons. So if you're dealing with something that is a neutral atom, the number of protons and the number of electrons should be the same, because all the positive charges in the atom will be balanced out by all the negative charges in the atom from the electrons. So if you have 3 protons, that's like a +3 charge. And you have 3 electrons, that's a -3 charge. +3 and -3 equals 0, right? They cancel each other out. Neutral, no charge when it's all said and done. It is also really, really important, though, if you're asked this question, which you might be asked, what is the definition of the atomic number? The actual definition is only protons. Yeah, so that is the actual definition of the atomic number, the number of protons. Separate to the definition is if you're dealing with something that's neutral, it will also tell you the number of electrons. But the number of electrons is not part of the definition of the atomic number. It is only the number of protons. And one case where that is, reason for that is you can have different numbers of electrons and same numbers of protons. So that is not the definition. Now, when we look at the periodic table, like behind me, that is our friend. We'll go with hydrogen, for example. That is lucky number 1 there. You can find the atomic number on the periodic table. It is the number that comes above the symbol on the periodic table. All these numbers up here above every single symbol is an atomic number. So hydrogen would have 1 proton, right, as its atomic number. If you had a neutral hydrogen atom, it would also have 1 electron to balance it out, right? We look at our friend nitrogen there. Nitrogen is lucky number 7. That is its atomic number. That means that it has 7 protons. And again, if you're dealing with a neutral nitrogen atom, it should have a matching number of electrons to cancel those out, and it would have 7 electrons. Now, when we look at the periodic table, you're the one up here, if you got one at your desk, do any of the top numbers repeat? They do not. Every single element has its own atomic number, which means every single element has its own number of protons, right? Which matches the atomic number. If you know the atomic number, or you know the protons, which is essentially the same thing, all you need is a periodic table. You'll know what element you're dealing with. You just go find the right number on top, and it'll tell you what element you're dealing with. Also, if you know the element you're dealing with, but do not know the number of protons, you just go to the periodic table, find that element, and look at the number on top, and it'll tell you how many protons there are. Question on that. Double Jeopardy question is, since every element has a different number of protons and atomic number, out of protons, electrons, and neutrons, which one is the most important in terms of what element you're playing with? It is protons, yeah? That is why what I just said a moment ago in nuclear reactions, all you do in nuclear reactions is play with the stuff in the nucleus, which means you change protons into neutrons, neutrons into protons. That is why you don't in a nuclear reaction have the same element you start with, because it all involves the nucleus and changing protons to neutrons, neutrons to protons, and you end up with different elements. In chemical reactions like we deal with, we only play with the electrons, which are on the outside. We never touch the protons. And because you never touch the protons in a chemical reaction, you always have the same elements you start with are the same elements you end with. They just end up in different locations or different places because they make different bonds, which involves electrons. But because you don't do anything with the nucleus, don't do anything with those protons, you never change the element. So that's why we have that conservation of mass. That's why we never change elements from beginning to end when you're dealing with chemical reactions. That's because I can never have a nitrogen atom that has 3 protons, right? Because who has 3 protons? Yeah, it's lithium, right? Lithium is the one with 3 protons, so it can never be a nitrogen. Yeah. So it can never ever change those things. So if you change the protons, then you're changing the element you're dealing with. So if you for sure know I need to keep this element, you should never touch the protons if you're doing some type of problem and change the number, because then you just change what element you're dealing with. Any questions on that there? Another really important number is the mass number, sometimes abbreviated with an A. The mass number is actually the number of protons and the number of neutrons there are in the nucleus of an atom. So the mass number is our number of protons plus the number of neutrons there are in an atom. Why is mass number kind of important? Well, if you take the mass number and you take the atomic number we just talked about, which is the number of protons, and you subtract them, protons go away, leaves you the number of neutrons. So if you take the mass number and you subtract it from the atomic number, that will tell you how many neutrons you have, basically. Yeah. When you calculate all these things that we're talking about here, when you calculate the atomic number, when you calculate the mass number, when you calculate how many protons, electrons, neutrons there are, they all should be positive whole numbers. So they all should be positive whole numbers. That brings us to the important question of, when I look at the periodic table, there are other numbers there. Like we'll take hydrogen. Well, we know this top number is the atomic number. Is the bottom number the mass number? 50-50 shot. Going to be wrong twice if you guess twice. Actually, a 50-50 shot, you can't be wrong once, I suppose, right? What do you think? Yes, no? The answer is no. Yeah. So once again, when you calculate the mass number, the atomic number, protons, electrons, and neutrons, they all have to be what type of number? Positive whole numbers. If you take a look at a periodic table, pretty much every single number on the bottom for all the elements, they're decimals. Yeah, they're not whole numbers. Yeah. That is actually not the mass number. That is what we'll talk about shortly, known as the atomic mass, which is not the mass number. So the only number that you could find on the periodic table is the atomic number. Why do people not believe me? Well, they don't believe me because when they look at that number on the periodic table and they look at the mass number, they're oftentimes very, very close to each other. And what a very common belief that people think, which is incorrect, by the way, is people think, well, they must have just rounded the number, and that's why I got a whole number here. That is not how you get that, by the way. So don't be the person that starts writing decimals for the mass number, because you don't want to be the person who gets the X's. Yes, so don't do that. It's not a rounded number or anything like that. So how do you figure out the mass number in these type of problems? You'll have enough information given to you that you could actually calculate the mass number. So either they'll tell you the number of neutrons, which will allow you to know the neutrons, and then you could go find the protons on the periodic table, add them together, you'll get the mass number. They may give you the mass number, and then you could subtract the number of protons, and it'll give you the number of neutrons. But again, you cannot get the mass number from the periodic table. It is not just like a rounded version of that number. So make sure you don't use that. That is a very, very common error that people make. Yeah. Any questions on that there? All right. Now, in most cases, atoms of a given element do not have the same mass, and that is what isotopes are. So isotopes and the existence of isotopes, as I mentioned, is one of the things for Dalton's atomic theory that kind of disproved one of his points. And basically isotopes are the same element, but they have different masses. So once again, in order for something to be the same element, which thing cannot change? Protons, electrons, or neutrons? Protons. So protons can't change in isotopes. So what gives them the different mass is they have different numbers of neutrons. And the reason for that is, again, neutrons are the heaviest of those particles. Electrons are not that big of a mass. So it is actually the number of neutron differences that give these guys their different masses. So isotopes are the same element, but have different masses because they have different numbers of neutrons. Every single element has protons, electrons, and neutrons except our friend hydrogen. Hydrogen has a proton. Hydrogen has an electron. Hydrogen does not have a neutron. So hydrogen does not have a neutron. It has proton and electron, no neutrons. But every other element will essentially have both, all three of those things, protons, electrons, and neutrons. When we write isotopes, we can include the mass number and the atomic number, and the mass number's upper left of the symbol, and the atomic number is lower left of the symbol where we place them. So for example, if we look at hydrogen, it has, as I just mentioned, one proton and no neutrons. Deuterium, which is sometimes referred to as heavy hydrogen, has one proton and one neutron. And tritium is the radioactive version of hydrogen, has one proton and two neutrons. So if we wanted to write the symbol for each of these isotopes, we would go about it this way. The proton here is the most important thing, right? Because that is basically the atomic number. And that means I could go to the periodic table if I'm not sure, find number one. And number one, once again, will say hydrogen, right? And that is the symbol that you should use. I also know that the atomic number should go bottom left. And that is what we should put there. Now, my mass number, right, is the number of protons plus the number of neutrons. So for hydrogen, 1 plus 0 is 1, and that's what should go up on top, and that is my mass number. So when you have an isotope written in this form, if you take the top number on the left minus the bottom number, that will give you the number of neutrons, right? So 1 minus 1 in this case is 0. That would be the correct symbol there for hydrogen. Now you get to something like deuterium, which to you and to me both does not sound like hydrogen. But I know it's hydrogen because how many protons does it have? It has 1, right? So I go back to my periodic table, that's still 1. So even though it says deuterium, I know really this guy is still hydrogen, right? Number 1 on the periodic table. And we could do our atomic number. To do our mass number, we're going to take our protons and neutrons. 1 plus 1 in this case is 2. And this would be our symbol for deuterium, which is basically still hydrogen, right? And it's still hydrogen because it has 1 proton. Those two have different masses because the guy on the right has an extra neutron, right? That the one on the left does not. It's actually heavier, which is why it's sometimes referred to as heavy hydrogen. Yeah. Question? Yeah. Yeah, so this is specifically for isotopes. So when you're asked, for example, to write the isotope symbol with like the mass number, atomic number, that's the typical locations where you put those two numbers. Exactly. If you were asked just to write like hydrogen, for example, the symbol not involving mass number or atomic number, you would write H2 on the bottom, and that would be the chemical formula for it. Yeah. Other questions? Now we come to tritium, which again doesn't sound like hydrogen at all. This is the radioactive version of it. But we again know it is still hydrogen because it still has one proton. And the only element that can have one proton is hydrogen. And again, we know that we should use that symbol as well. So again, with isotopes, you may come across things that don't have like the element name. But again, when you look at how many protons it has, you can definitely determine what element it's dealing with, because as we just talked about, every single element has its own atomic number. So whatever number of protons it is, it's got to be that element based on the periodic table. So once again, we go on the bottom here, we will do, through all my scribble, 1 plus 2 there is 3 for our mass number. And that would be our symbol there for tritium. Again, even though they all three have different names, they're all essentially the same element, which makes them isotopes. They do all have different masses because we take the top number minus the bottom number on the left. That's 1 minus 1, which is 0 neutrons. Deuterium in the middle, 2 minus 1 is 1 neutron. And tritium at the end there, 3 minus 1 is 2 neutrons. They each have different masses, which is basically your definition of an isotope. Same element because they have the same number of protons, different masses because they have different numbers of neutrons. Any questions on that there? This is probably a very common way that isotopes are written. There's also another way that isotopes are written. For example, if I go with Cu64, that is copper 64. I know Cu is copper because I studied my periodic table, I suppose, right? And my elements and my symbols. I want to know what the 64 represents, right? Well, I could do it by process of elimination, right? If I go to my periodic table and I find copper, I got something that looks like this. Is the 64 the atomic number? It is not, because the atomic number should be 29, as we see from the periodic table. So this is clearly not the atomic number of the 64, which leaves it only to be the mass number. Yeah, so that's a very common way that isotopes are sometimes written. It's like the symbol dash a number. The number that comes after that dash in this way of writing isotopes is the mass number. If we want to kind of write it the other way, we would use our symbol for copper, which is Cu. We would use 29 on the bottom, which is our atomic number, and up on top would go our mass number, which is 64 in this particular case. Question on that. So sometimes radioactive guys are written that way. It's very common way isotopes are written. By the way, that would mean my copper here has how many protons? It does have 29 protons, right? Or 29. It is neutral. By the way, how do I know it's neutral? I would look right there and I don't see anything, right? I don't see a positive charge, a plus, I don't see a minus. So it's safe to assume that it's neutral in this case. And because we are assuming it's neutral because we do not see a charge, that should mean how many electrons do I have? 29. Once again, 29 positive things and 29 negative things gives you a bagel, goose egg, 0 there, right? No charge, it's neutral, right? And that is, what balances out. How about my neutrons in this case? Number of neutrons would be my mass number, which is 64 in this case, minus my atomic number, which is 29. And it's been a long day, so I'm going to look at the calculator. That's 35, I think, here for neutrons. It would have 35 neutrons. Any questions on any of those there? So again, I would say probably in this class and most classes, this sort of way is probably how you would write the mass number and atomic number. But the other way with the dash, that does pop up a lot, especially if you're looking at something that's sort of radioactive. So sometimes they like to do that. Sometimes in books they like to do that as well. It's a lot easier to type that in than like the two superscript subscripts. So again, if you see it the other way, it's most likely going to be the mass number. You can easily verify that by looking at the periodic table and seeing it's not the atomic number, right? So if it doesn't match that number, then you definitely know it's not. All right, so why don't you give it a go here for each of these. Okay, so let's take a look, see how you're doing. We'll start the first one, CO, which is, by the way, cobalt, right? The element. So clearly in this case, the easiest thing to figure out right off the bat is the number of protons, right? That again should be our bottom number here, which is our atomic number. And once again, our top number would be our mass number, which is the number of protons plus the number of neutrons, while our mass atomic number is the number of protons. So we know here it definitely has, in terms of protons, 27 positive guys. We also could see here nothing written upper right, so we do know it's neutral, which means it should have a matching number of negatively charged electrons, right? Again, 27 positive protons along with 27 negative gives you that zero charge or neutralness that is there. For our number of neutrons, we're going top number minus bottom number, our mass number minus atomic number. So number of neutrons here, mass number 60 minus atomic number 27, 33 looks like a winner in that case. Any questions on that there? Looking at the next one, Cl is chlorine. So once again, probably the easiest to start with is our protons, which has how many? Does have 17, which matches the atomic number. Once again, we do not see anything written there, so we know it is neutral. Again, you would see like a, +2 or -1 or something like that, written there. So we then automatically know we got to have a matching set of electrons. And our neutrons in this case, once again, going to take our top number, which is our mass number, minus the bottom number, which is our atomic number. And that's going to give us a 20 in that case. Lastly here, U is uranium, perhaps probably the only one on the bottom here that we might come across. So uranium does pop up occasionally. We got 92 there for our atomic number. So number of protons is 92. Once again, nothing written there tells us equal number of electrons to balance it out, giving us our 0. Our neutrons there's a lot. Those 238, which is our mass number, minus a 92, buck 46, I think, right there. Yeah, 146. We should be good on that. Any questions on any of those? I'll try a few more here, see how you're doing. On these, we want to write the symbol with the mass number and atomic number for each of these. In case you don't have a periodic table located that you can see, since I'm standing in front of it, let me draw. Okay, let's take a look and see. So obviously krypton, you would need to go to the periodic table and find it, and it is Kr. So that would be the symbol that we would want to use. Obviously, as we talked about from the periodic table, we could get the atomic number, which should be the number up on top. That on our symbol there is going to go bottom left. We do need to know the mass number in this case, which would go top left. In this case, we are given the number of neutrons, and we want our mass number, which again is our number of protons plus the number of neutrons. We now know our number of protons from the periodic table is 36. Our number of neutrons was given to us, which is 48. Looks like an 84 should go up there on top. Any questions on that one there? Looking at the next one, which is nitrogen. And nitrogen is N. And again, that is the symbol we want to use. Once again, from the periodic table, we can always find the atomic number. which is our number of protons. So we could go with 7. Again, that's going to be helpful because now we know in terms of protons, it has 7, and they gave us neutrons, it has 6. So 7 plus 6 will give us our mass number in this case, which looks like a 13 here. Any questions on that one there? Lastly, we have iron over here, and in this case, it actually gave us the mass number. So we would go Fe. And our mass number was 56 that they gave us, should go up on top. Once again, from the periodic table, we could get our 26. They also want to know, in this case, protons, electrons, and neutrons. So iron, in this case, has how many protons? 26, yeah. Electrons, it has 26 as well. Again, no charge, right? It doesn't say anything about a charge in the writing. So you could safely assume that it's neutral in this case. Neutrons in this case would be 56 minus 26, right? Mass number minus atomic number 30 in that case. Yeah. Any questions on any of those there? Mass number, atomic number, protons, electrons, neutrons. Any questions? All right, while we have it, I know the question you want to ask. What happens if it has a charge? You wanted to ask, didn't you? Somebody wanted to ask something. All right, so let's talk about why we have this. What would happen if something did have a charge? So I'm just going to steal this page here, I think. And we'll borrow some of these guys. I think. So first off, if we do have something that has a charge, that is what is known as being an ion. So an ion is something with a charge. And there's actually 2 types of ions that we come across. There is everybody's favorite, it's a cation. Those are positively charged. And everybody's other favorite, which are anions, which are negatively charged as well. Yeah. So how do we get to the positive charge or negative charge? So let's try to think about what would give us a charge. So if we take our nitrogen here, which clearly at this point has no charge that we just dealt with, and in the case of this neutral nitrogen, it would also have obviously 7 electrons as well, right, to balance it out. If we take nitrogen, which has a tendency to make a -3 charge, and we'll even roll with the same numbers here. Now let's see what is affected when it does have a charge. So clearly here, because that is nitrogen with the charge and the guy with no charge is nitrogen, what number should not change? It still is 7 protons, right? So as we talked about before, you cannot change the protons. Otherwise, it would, in this case, no longer be nitrogen. So clearly we know it cannot get its charge from changing protons, right? Otherwise, it changes elements. We also know that proton is 1 of 3 particles in an atom. So we can't change protons to get a charge. You can choose the right finger there. We cannot change neutrons because they have no charge, right? And that's not going to affect anything. You can do whatever you want with neutrons. It's not going to change anything. That leaves only one thing that affects charge, and that is electrons. Yeah, so it's actually the number of electrons that affect the charge. We can see that even here, number of neutrons in this example, 13 minus 7, still 6 like we had over here, right? That doesn't change. Protons doesn't change. It is actually those electrons that change. Now, in order to give my nitrogen in this example a -3 charge, how many electrons would I need? I need a total of 10 electrons in this case. That's because I now have 7 positive protons. I have 10 negative electrons. 10 negative things plus 7 positive things leaves you a -3 left over. And that is where the charge comes from. Because in this case, you now have more electrons than protons, right? So you got an excess amount of negatively charged electrons in this atom, which is giving it a overall -3 charge. So this is an anion, right? Because it's negatively charged. And the way that we get negative charge is something needs to gain electrons. That is what the negative means. When you see a negative charge, it means that thing has gained electrons from its neutral self. Yes, from its neutral self, it had 7 electrons, and its -3, it has 10 electrons. How many electrons difference is that? If it has 7 to start with, ends with 10, how many more electrons is that? Where do I see 3? In the charge, right? That's what the number indicates. It indicates how many electrons, in this case, the nitrogen picked up from its neutral self, or from somebody else really, but the change from its neutral self to where it has now a -3 charge is it picked up 3 electrons. So when you see a charge and the number associated with that charge, in the case of a negative charge, the number tells you how many electrons that substance picked up from its neutral. It went from its neutral to that, and the negative tells you that it gained those many electrons. Question on that there. So if we take a look at iron down here, and we take iron, one of the charges iron could do is a +2, for example, and we'll do the same numbers. So clearly, just like we were talking about, the number of neutrons won't change in this example. 56 minus 26 is still 30. We know the number of protons still has to be 26 because it's still iron. So the number of protons in this case is 26 positive guys. Has a +2 charge, which means it's a cation. How many electrons would it have in this case? 24. Yeah. 26 positive protons and 24 negative electrons leaves you a net +2 left over. And that, once again, is where the charge comes from. In this particular case, the opposite is true. It actually has more protons than electrons in this case. And now it has a positive charge. Because of that, it has an abundance of protons and positive charge versus its negative charge electrons. That was achieved if we look at comparison between the electrons in iron with a charge and the electrons with it no charge. Is it actually lost electrons, and that is how you become positively charged. You will lose electrons. So when you lose electrons, you have more protons, you become positively charged. When you gain electrons, you now have a lot more negative electrons, you become more negative. Yeah, so when you lose electrons, more positive, gain electrons, become more negative. Question on that there. So the only thing that changes is the number of electrons when somebody either gains a charge that's positive or negative. It's only the electrons that change. A free radical is actually something different. We may talk a little bit about that in a later chapter, but a free radical actually is a species that has one unpaired electron, and it makes it really reactive because it doesn't really want to be that way. Yeah. What actually, the way this actually occurs, by the way, as I talked about earlier, is none of these guys, none of these elements, right, as I talked about in their neutral state, have a charge. But if you were, for example, to throw together like the iron and the nitrogen, the iron will actually lay up his electrons and give them away, and the nitrogen will pick them up. And that's how these things gain charges. Basically, what happens is they make an ionic compound, and usually it's metals, by the way, which we'll talk about in this chapter as well. Metals over here on the left-hand side of the periodic table. They are typically the ones that will lose electrons. And for reasons we'll talk about also in this chapter at the end, why they do that. They're pretty much, you don't have to convince them all that much to give away their electrons. They're like ready to give them away. Non-metals, which are actually over here, for example, on the periodic table, those guys are all about keeping their electrons, and not just keeping their electrons, but taking electrons, bringing electrons towards themselves. And that is why, for example, when you take a sodium and you put it near a chlorine atom, this is a metal, this is a non-metal, and this chlorine, as we'll talk about in the next chapter, basically is starting with, if all those dots are electrons, they have 7 what is known as valence electrons. Sodium has one little valence electron. And when those two guys get together, because of some of their trends and their periodic properties, this sodium's just going to go take it. Yeah, just go ahead and take that electron, not a big deal. And the sodium, as a result of giving away its electron, will then become sodium with a +1 charge. The chlorine, which now goes, cool, thanks, gained an extra electron. So it now goes from neutral to I have a charge. And now we have what we talked about at the very beginning, go full circle here in the last few minutes. We have something that's positively charged, right? And negatively charged, which means they're going to want to come together, right? They're going to want to bond with one another. And that's how we get our famous salt there, right? A little sodium chloride action. And that is how they come together to actually form something like an ionic compound, which is what that is. But before they come together, neither one of them have a charge. But it's only really the presence of them being near each other that it kind of initiates that go ahead and take my electron and I want your electron. And that's where we get that transfer of electron that happens. And we'll talk more about that obviously in the bonding chapter, which is next chapter. I think we're going to get into some of that question on that there. Why don't you try one? Why don't you do let's go nickel with a +4 charge. Let's do oxygen with a -2 charge. And in terms of the periodic table, nickel is 28 and oxygen is 8. So for each of these, how many protons, neutrons, and electrons are there in each of those ions? Take a moment and calculate it. Okay, so let's take a look. So once again, I guess I should have put some numbers for the neutron part. That would probably be more helpful, I suppose. All right, so let me actually do that real quick. We'll throw some numbers that you might need, I suppose. So let's just go with 60 up there, and we'll go 8 and 16. All right, find your neutrons now. All right, so let's see what we come up with now that we have numbers. That might be helpful. All right, so in this case, obviously here for our nickel, we have our number of protons should match our atomic number, which we again could get from the periodic table, and that should be 28 here. Obviously, our number of neutrons in this case is going to be our mass number, which is on top that we now have, and our atomic number there, and that's going to give us 32. This is a cation or anion, this one? It is a cation. I know that because it's positively charged. I also then should know, did it lose or gain electrons? Did it lose electrons? By the way, even without calculating, I know how many electrons it lost. How many? Lost 4, right? That's what the number represents, right? So in this case, we need our number of electrons to reflect that. And in this case, we would actually have 24 electrons. 28 positively charged guys, right? 24 negatively charged guys. Gonna leave us a net of a +4 left over, which again is where our charge comes from. In contrast to neutral nickel, with the same numbers there. Neutral nickel would have 28 protons and 28 electrons, right? So we could see once again, as we talked about, from its neutral self, it dropped 4 electrons pretty much, right? And again, at this point, it now has more protons, which are positive, than negatively charged electrons. So it's got a net extra, if you will, 4 protons, given it is +4 charge. Any questions on that one there? All right, oxygen here. Again, our number of neutrons going to be mass number minus atomic number, which will be 8. Our number of protons going to match our atomic number, which is 8. We know that this guy is an anion as it's negatively charged. Should mean that it has now gained electrons, right? And the number of electrons it gained is 2. By the way, all you have to do in that case is add 2 to the protons, right? So Number of electrons is 10 in this case, right? Given it -2 left over, 10 negatives, 8 positives, leaves you that left over. By the way, knowing that this guy lost 4 electrons, right, means you could just subtract that from the atomic number, right? Because in a neutral guy will have the same number of electrons, right? So you can just subtract it in that case. Again, in comparison to neutral oxygen, it would be number of protons 8, number of electrons 8. So 8 in neutral, 10 in the guy with the charge, again gaining 2 electrons. Any questions on how to do it with charges? So once again, only electrons change. Any questions?